In this section of our unit, we're going to discuss the formation of alkanols. Alkanols can be produced through a variety of reactions from a wide range of starting materials. Alkanols themselves are often used in industry as a starting material since they can also be used to form many other compounds. The hydroxyl group, remember from your naming organic compounds, the hydroxyl group is the OH group. So that OH group on the alkanol is a reactive site that allows the alkanol to be converted to a variety of other functional groups. Below in this image, you can see a summary of the different functional groups that can be used to form alkanols or can be formed from alkanols. So if I have this OH group, I can form several different compounds with different functional groups: halides, alkanoates, carboxylic acids, alkenes, alkanones, alkanals, ethers. Similarly, we can go the other direction. If we start with an ether, we can form an alkanol, and so on and so forth. Ethanol is commercially significant and widely produced in industry. Ethanol has two commercial uses. The standard uses for ethanol are as a beverage for human consumption and as a fuel. Common ways of preparing alkanols are listed below. First, fermentation, specifically used in the production of ethanol. Second, the reaction of an alkanal or alkanone with a Granular reagent. Third, hydration of an alkene. And fourth, the catalytic reduction of an alkanal or an alkanone. We're going to discuss each of these common preparations in the following slides. The most commonly used method of producing ethanol in industry is through the fermentation of molasses. So fermentation will be the first process we discuss. The two steps of fermentation are performed with the help of enzymes invertase and zymase from yeast. The first step involves the hydrolysis of sucrose or sugar, forming glucose and fructose. Hydrolysis is a reaction where a water molecule breaks one or more bonds of another molecule. The yeast supplies the enzyme invertase, which catalyzes the hydrolysis of the sucrose. In the second step of fermentation, glucose and fructose are decomposed to ethanol. The enzyme zymase, also supplied by the yeast, acts as a catalyst for the second reaction. So in step one, we have our sucrose that we hydrolyze with a water molecule and the catalyst invertase to produce glucose and fructose. Then we take the glucose and fructose molecules in step two, and with the enzyme zymase to catalyze the reaction, we decompose this into ethanol and then CO2 as a byproduct. All right, another method of preparing ethanol is the fermentation of starch, typically found in materials such as tapioca, maize, and potatoes. The way this reaction or this fermentation process starts is we take one of those starches, we form a paste in water, we mix it with malt extract or germinated barley, heated to 50 degrees C. This process, just like the one we talked about previously with the fermentation of molasses, also involves a two-step reaction. The first step is catalyzed by the enzyme diastase, which is present in the malt. So that's why we are using that malt extract. is for the enzyme diastase. With diastase, then, what it does is it hydrolyzes the starch to maltose, which is a disaccharide. So I'll show you that on the next slide. So step 1 in the process is to take our starch water paste and the malt extract, which provides that catalyst to produce this disaccharide maltose. Okay? Then yeast is added to the maltose. There's an enzyme present in the yeast called maltase, which converts this maltose into glucose. And then zymase will convert the glucose from this maltose, forms glucose. Zymase in the same step will convert the glucose to ethanol or ethyl alcohol. Another way of producing alkanols is from an alkanol or an alkanone using something called a Granular reagent. A Granular reagent is an organomagnesium compound. It is a substance that consists of a hydrocarbon radical, like magnesium, and a halide, like bromine or iodine. The Granular reagent is prepared from an alkyl bromide, so a hydrogen-carbon chain with a bromine on it, and magnesium in an ether solvent. Okay, when you use a Granular reagent, the type of alkanol formed depends on the alkanol or alkanone used in the reaction. So let's take a look at this. In this case, the double bonded oxygen carbon, the carbon is bonded to 2 hydrogens. When it reacts with the Granular reagent, which is symbolized here, we get carbon bonded to the R group, still to the 2 hydrogens, and then single bonded to OH. This is a primary alkanol. A secondary alkanol forms when, let's take a look here, we have C double bond O, but then it's also bonded to 1H and then some R group, R prime, methyl, ethyl, any carbon containing group. So see how we've just reduced the number of hydrogens here because we have a chain of carbons also attached. When we do that, we get a secondary alkanol where we have carbon still only bonded to 1 hydrogen. This original alkyl group that was on the original reactant, the alkyl group from the Granular reagent is also bonded to this carbon. So we have C bonded to R prime, C bonded to H, C bonded to R, and then C single bonded to OH. So this is a secondary alkanol where we have only 1 hydrogen and 2 R groups. Now, if we have no hydrogens, if the original reactant has no hydrogen, so we have C double bonded to O, and then also bonded separately to 2 R groups, 2 carbon containing groups, which we're calling R prime and R double prime. When we react that with our Granular reagent, now carbon is single bonded to each group, R prime, R double prime, and R, and then also single bonded to OH. So this is a tertiary alkanol because there are no hydrogens, right? Carbon is bonded to 3 other carbons here. This carbon is bonded to 2 other carbons, right? And this carbon is bonded only to 1 other carbon. Symbolized, of course, by these R prime, and R double prime. Another way that we can form alkanols is through the hydration of alkenes. So I have 2 examples here where we hydrate an alkene. So remember that a hydrate means to add a water. So we break these bonds by adding a water here, right? This hydration idea. So look what happens We're going to use H2SO4 to do it. So we have CH2, double bond CH2. We're going to break this double bond through the hydration, and then we need to add a water. So CH2 becomes CH3, single bond to CH2, single bond to OH. So there's our hydration. There's OH there, and then one H was added here. So there's our H2O. All right. Same thing in the second example. We just have a longer chain to start with. So CH3, single bonded to CH, double bonded to CH2. We're going to use H2SO4 to hydrate this double bond. So we're going to break the double bond. We have a single bond. We're going to add one hydrogen here. And so now we have CH3, single bond, CH2, single bond, CH2, and then single bonded to the OH for our hydration of that double bond. The last way we're going to talk about for how we can form an alkanol is through the reduction of a carbonyl compound. Alkanols, so remember that a carbonyl compound is one that contains C double bond O in some form. Okay, that's a carbonyl compound. So alkanols and alkanones contain that C double bond O, and they can be reduced to the corresponding alkanols by the addition of hydrogen in the presence of metal catalysts such as finely divided platinum, palladium, nickel, and rubidium. This can also be performed with reducing agents such as sodium borohydride or lithium aluminum hydride as shown. So here's a couple of examples for the formation of either primary or secondary alkanols. So if we start with this material, RCHO, so again, carbon single bonded to the R group, single bonded to the H group, double bonded to the oxygen, so that we have a carbonyl group. In the presence of hydrogen and a metal catalyst of some kind, we reduce this double bond. What happens here is where we have C double bond O R H. Now we have R C O H H H. Okay? So through the addition of that hydrogen, we're able to reduce that oxygen to create the primary alkanol in this case, because the carbon is bonded to only one R group and two hydrogens. Now we can do the same thing in the second reaction. In this case though, instead of being bonded to a hydrogen, we're bonded to two R groups, okay? But we can still, through the addition of this hydrogen with a catalyst, we can reduce this oxygen to form OH, and then we also have to add our hydrogen here. Now in this case, you see how the carbon is bonded to two R groups, so two other carbons, which is why we call this a secondary alkanol. So the distinction we can make when we're talking about reduction of a carbonyl compound is depending on where that carbon double bond oxygen group is, will help us determine whether or not we're forming a primary or a secondary alkanol. Now, remember that alkanols have the C double bonded to the oxygen on a terminal carbon. So that would be the three examples on the left. This is a terminal carbon. It's the only carbon, right? C double bond O, and then bonded to two hydrogens. Here, this is on the terminal carbon, C double bond O, H. Same here. This is on the terminal carbon. In every one of those instances, we're forming primary alkanols because the carbon that bonds to the OH group is only bonded to one other carbon. Okay? If the double bonded oxygen is in between two carbon-carbon chains. So in this case, we have a CH3 on the left and a CH3 on the right. In this case, we have C2H5 on the left, so an ethyl group, and a methyl group on the right. So in this case, this carbonyl group is not a terminal carbon, and so this is an alkanone, right? In that case, we're forming secondary alkanols because the carbon containing the OH group is bonded to two additional carbons.